Oh.
Practice and drink water all day. All I'm saying. That darkness, like that water right out anyway, you just. Oh, like crazy.
All right. Couple of things to mention before we get started. Let's start with the good news here, which is that you guys did exceptionally well on the most recent quiz. I think the average was sitting around like an 84, 85, which is perfect. That's super, super good. So very, very well done on that. That's a lot more in line with what I expect of you guys. Now, this class in particular has actually been doing a fairly good job, or a fairly decent job at least, through units 4 and 5. But especially with my other classes, that was much more in line with what we were expecting, which is awesome. All right, quick point that I would like to mention. I am currently missing 3 calculators, which I need those calculators. So what we are going to do is starting tomorrow, if I do not have those calculators back, we're going to start implementing a checkout system, which would essentially look like you turn in your phone for a calculator. It is not something that I want to implement, but I need my calculators back. So if you have accidentally taken one home or taken one home to work and have just forgotten to bring it back, then make sure that you have it in, bring it back by tomorrow. All right. So today, yes. SDC test, I believe, is so I think we start testing on a Tuesday. I think it's like the 16th. Our test is the 17th. It's the second day of testing. I think it can get you exempt from the final, is how it works. However, SDC tests normally work. I'm pretty sure the way it works is if you pass, then you don't have to take the final for this course. And if you don't pass, then you do have to take the final for this course unless you're exempt through like grade and absences. Any other questions? We're going to start reviewing. I mean, we already started. We did a little bit of the Unit 1 stuff already. We're going to start reviewing in earnest after tomorrow. Tomorrow will probably be the last like new piece that we learn before we start taking a look at some of the old stuff. Okay. Okay. Let us take a look then at 6.2. Should hopefully be fairly straightforward, would be my guess. I do, before we talk about 6.2, I do want to redact something that I said earlier. So 6.1, what we were working with before, this idea of confidence intervals for the mean, there was an assumption that I said that we were making. And while, yes, we are going to see that when we make that assumption, things work for us, it's a little bit too narrow of a definition for what I would like. And so we're going to broaden it ever so slightly. What was the condition that our sample needed to satisfy in order for us to be confident that we were working with a normal distribution? In other words, what allowed us to be comfortable using z-scores? What condition did our sample have to meet? sample size had to be more than 30. That is true. It is true that if our sample size is more than 30, that we are working with a normal distribution, which is cool. That's like an element of the central limit theorem. That's what we've seen. But that's also a little bit too restrictive. The cool thing about the greater than 30, when that's our sample size, is that that doesn't care about the true standard deviation. And it also doesn't care about the sample distribution that we're pulling from. So we could, for instance, be pulling from a distribution that looks like this. And if we collect, if our sample is 30 or more, then it's going to be coming from a normal distribution, which is fairly cool. If, however, we already know that the distribution that we're pulling from is normal, and also already know the population standard deviation, then we don't even need a sample size of 30 to be confident that what we are looking at is in fact a normal distribution. So yes, when we are greater than 30, certainly we are basically a normal distribution. When our sample size is greater than 30, that is true. But even when we are less than 30, if we're pulling from a normal distribution, and if our standard deviation for our population is known, that's over. Thank you. Afterwards, all right, so slight adjustment, which is confidence interval for our mean. This is if sigma is known. And the variable is normally distributed. Well, then we saw for our confidence interval, this was x bar minus the EBM up to x bar plus the EBM, where EBM is just like a fancy way of saying error or margin of error or what have you. This is the margin of error. And then the way that we computed margin of error, this EBM, was just the z-score that we found times sigma over the square root of it. Z of alpha over 2. What does the alpha over 2 mean again? Why do we say z of alpha over 2? So why is it alpha over 2? So in between, we have how much? Let's say this is a 95% confidence interval. How much do we have in between our z values? 95%, which means how much do I have on the outside? 2.5% on each side. So it's alpha over 2 because we take that area on the outside and we're splitting it in half. Half of it on the left-hand side, half of it on the right-hand side. So T of alpha would be a one-tailed test, or Z of alpha. Sorry, we're not doing T yet. So Z of just alpha would be saying, hey, we've got 5% on this side and 95% on this side, and there isn't a second z-score that we are working with. Take a look at the video that I uploaded on Thursday if you have not yet to look at that. That's part of what we dealt with the hypothesis testing stuff. Okay. But essentially z of alpha over 2, this is just like the z value that we have been using up until this point. And the alpha over 2 is just to say, I'm going to get one z value that is going to be on my left-hand side. It's going to be negative. I'm going to get one z value on my right-hand side. It's going to be positive. The absolute values should be the same. They should be equidistant from one another. Now, however, we are going to be zooming in a little bit. Not only are we not going to know the standard deviation of the population, and not only are we not necessarily going to know that our variable is normally distributed, we're not going to have a large enough sample to be able to use z-scores. So this is if our sigma is unknown and n is small. Again, what's our cutoff for small? N is less than 30. Yeah. Then what we are going to see is actually basically the exact same thing. This is still going to be x bar minus the error to x bar plus the error. And in fact, even the way we calculate the error is very, very similar. But we have a slight issue, and that is that because our sample size is too small, we are not guaranteed to be pulling from a normal distribution. So we don't know if this sampling is going to be taken. We don't know the shape of the distribution that we're pulling from. That is going to reduce our confidence. I don't know what sample I'm looking at. How can I be 95% sure with the same level of gusto that we were seeing from my z-scores, from what we were doing before? In order to offset the loss of confidence that we have from just not knowing what distribution we're pulling from, we're going to need to use a slightly different score than a t-score. It's going to be a little bit bigger. A little bit bigger, mostly just because of the fact that we're a little bit less sure. And so because we're a little bit less sure, we need to lose a little bit of precision. So our margin of error is going to be a little bit larger. It's going to be a little bit wider because we don't know what distribution we're pulling from. This score that we're going to be using, that is, again, going to basically be taking the place of our z-score. We just, again, don't know that we can use a z-score, is going to be called a t-score, in particular denoted t of alpha over 2 for the exact same reason that we had z of alpha over 2, right? It's going to be like we have 2.5% on one side, 2.5% on the other. Exact same idea. Now, normally, we would like to do this like times sigma over the square root of n, but part of this is that we don't know what sigma is, right? Sigma is unknown. So we're going to have to do the best with what we've got. I don't know what sigma is, but I can guess as to what sigma is by using the sample standard deviation. And again, adjusting for my taking a sample by dividing by the square root of n. So basically, it's a z-score, right? Or rather, it's a z confidence interval, except we don't know the standard deviation of the population. So we have to substitute using the standard deviation that we got just from our sample. And then because that loses us some confidence, we have to use a different value. We can't just use the z value. We have to instead use this thing that's called a t value. Otherwise, exact same thing as doing confidence interval with z-score. Okay. Now there's a key idea here with our t-value. And this is why I say that once n becomes large enough, we can basically just switch back over to using z-scores. So once n is bigger than 30, we can make the switch, even if we don't know what sigma is, which is a little bit odd. But the main kind of driving principle here that we're going to find is that our t-scores improve with larger values of n. That is to say that our t of alpha over 2 gets closer and closer and closer to the z of alpha over 2 as n gets bigger. So by the time that n is 30, you're basically using the z-score instead of the t-score. Like you could still call it a t-score, but it's going to be basically equal to the z-score. By the time that n is 300, they're going to be almost indistinguishable from one another. But 30 is like close enough. It's like close enough to the point where we just actually just switch back to the z. Because our value of t changes based on the sample size, the table that we end up using for this requires us to take into account the size of our sample. So we didn't see this with z-scores because z-scores don't care. It's normally distributed. That's fine. Z-value is going to be the same no matter what. Here it matters, though. It becomes more and more normal as n increases, becomes closer and closer and closer to a z-score as n increases. And so we see different t values based on the size of our sample. These are converted. This is something that we saw before in Unit 1 into something called degrees of freedom. How did we find degrees of freedom for our correlation coefficients back in Unit 1? Nope. We didn't talk about R-squared. This is a lot simpler than this. So for instance, if I had a sample for my correlation coefficients that was of size 8, what did that correspond to in terms of degrees of freedom? And way back to Unit 1, or back to the review that we did like a week ago. I guess maybe it was 2 weeks ago. How did I find degrees of freedom? Much, much easier than anything that you'd use for the calculator. Very, very straightforward. Even easier than that. We're not talking about percent confidence or anything. I'm just saying, how did we convert 8 data points into a number of degrees of freedom for our Unit 1 stuff? You guys either need to be Googling or you need to be looking at your Unit 1 notes. I'm not answering this for you. Like, this is something that I need you to provide me. All right, figure it out. Go. I don't care for weaponized incompetence. Okay, so that would have been, so we'll talk about how we do this. For correlation coefficients, it was subtracting 2. So what we saw for our correlation coefficients here, and let me, oh, no, was that our degrees of freedom, this is not something that I would kind of note here, but this was degrees of freedom for R was n minus 2. But that is not set in stone. That is not something that is going to necessarily be consistent across all the types of ways that we are going to be doing this. And for our t-test, it is not n minus 2. It is what Abi said. It is n minus 1. Yeah, absolutely correct. So our degrees of freedom are very simply going to be the sample size minus 1. So before it was minus 2, which is just the way that it was set up. Now it's minus 1. It's just the way it's set up. questions with our formulas here? All right, let's take a look at our first example here. We're trying to find the relevant t-score, so t of alpha over 2, for a 95% confidence interval when our sample size is 21. So let's start just really quickly with the z of alpha over 2 at 95%. What is the z-score that corresponds with 95% confidence interval? 1.96? And so the idea here is, okay, we're going to need to figure out what is the t-score that corresponds. Yes. Yes. Because the t of alpha over 2 for the formulas that we get is always the positive version. Yes, both of those are relevant scores. We're going to see it's the exact same thing with t. We'll have a positive version and a negative version. We state the positive version. You will use both. So z of alpha over 2 is the positive version. Yep. Okay, how many degrees of freedom do we have? Yeah. 21 minus 1, 20. We're looking here. One-tailed versus two-tailed. So we haven't really talked all that much about one-tailed. If we watched the video that we were supposed to on Thursday, then we would have some idea of what's going on with the with one-tailed versus two-tailed. Confidence intervals are always two-tailed. We always have a little bit to the left of our confidence interval. We always have a little bit to the right of our confidence interval. That's two-tailed, two sides of what we are working with. And so how much confidence do we want? We want 95% confidence, or this one-tailed alpha of 0. Or this two-tailed alpha, sorry, of 0.05. And so what is the relevant t-score at 20 degrees of freedom? Well, that t of alpha over 2 is 2.086. So a little bit bigger, a little bit wider in terms of margin of error compared to the z-score, which again should be very consistent with what we're saying, right? We lose a little bit of confidence, so to gain it back, we widen our margins a little bit. In fact, what do we notice here as I increase my degrees of freedom? What happens as we go down this list? Yeah, it's getting smaller and smaller and smaller, and it is in fact converging to this 1.96. It's getting closer and closer and closer and closer to this 1.96 value. Okay. Now, of course, we're not going to be given t-tables on the SDC test because they hate us. And so we need to figure out, or maybe not really even necessarily figure out, but we're going to need to get this from our calculator. We're going to need to do this. How did I get the relevant z-score from my calculator? What did I have to do in order to get that? Yeah, so that was, how do I get there? So second vars, and before I was doing inverse norm. So what do we expect to do now that we're doing t-scores? Inverse t, right below it. Sure. Wow, this is quite the ad. They said, how about no more 5-second ads? How about the entire class is just ad? Fourth period got an enjoyable photo math ad, which was quite entertaining for me. Cool. Now, slightly different than what you have seen with your inverse norm is that we no longer have the ability to tell it that we want the area to represent the center or left or right. This is inverse T. Yeah, inverse T. So second bars, inverse T. You'll notice all you can say is area and then degrees of freedom. You don't have the ability to mention anything else. Yeah. And so our calculator is going to be doing what my calculator has been doing up until this point. There's no reason why yours shouldn't be able to do the center area, but fine, whatever. We're going to need to convert our 95% into an area to the left. It's what it's defaulting to, is the area to the left. So if I have 95% of my area in the middle, how much area am I going to have off to the left? 2.5%. So 0.025 is my area. And then what did we say for our degrees of freedom? 20 degrees of freedom. And we see exactly what the table told us already, 2.086. I don't understand the question. What's your question here? So second bars, inverse T, yeah. That means that you need to quit out. That means that you're doing inverse T inside of inverse T, and that's not going to work. Yeah, so you need to quit out of that. Now, that is giving us the kind of negative version, which is this T of alpha over 2 here, the negative T of alpha over 2. If I wanted to find the positive version, how much area is going to be to the left of this T-score that I see on my right? If I want the rightmost T-score, what should I put for my area here? 97.5. It's the 95 in the middle, as well as the 90, as well as the 2.5 off to the left here. And what we will see is if we do that, we should get the exact same thing, but it'll be positive, which is exactly what this is. It's the same number. Yeah. One's just negative, one's positive. What do you mean? Well, the T of alpha, just like with the Z-score, you give the positive version. So you're just going to take the absolute value, call it positive. Yeah. All right, give it a stab for the second example here. Trying to figure out the relevant T-score with a 99% confidence interval with a sample size of 8. Think, how many degrees of freedom do you have? What is the area that you would use? And so. So the only instance when I could get one tail was, did you do the hypothesis testing module yet? Okay, so with the hypothesis testing module, when you're looking at. Hey, I want to know if what I'm looking at is having a positive effect or a negative effect on the mean. Is the mean actually shifting to the left or shifting to the right? So if I wanted to, if my guess, if my alternative hypothesis, is that my mean is decreasing. Right, this is, I'm saying I know the direction, right? There's directionality to it. Well, then what I need to do is have 5% be over here and 95% be over here. This is one tail, because here I'm still finding fail. Like if I get a really, really big positive answer and an answer that's well above the mean, then I'm not satisfying this condition that I'm trying to satisfy. And so all my values over here are fail. It's only when we have success on one side of our kind of interval that we would have.
Maybe that's somebody's sister.
It's 90. What's that?
Yeah, that's perfect.
Yeah, so how do you get?
Set free.
So if we want 99% in the middle, how much is gonna be on the outside? 1%, and we have that split across on either side, so that'd be like 120%.
But what would you?
0.5 is 50%.
Oh,
Yeah, you're taking that 0.5% and then converting it into this.
Yes. That's with Leon.
So where is this?
That's
Yeah. So 0.5% is not 0. 0.0. Yeah, 0. Because you're. Yeah.
Oh, God.
Exactly.
They lock in. Everybody lock in, maybe explain over here.
That's what I'm asking. Degrees of freedom looks good. We don't need to worry about it. See, sort, you're just trying to use your calculator. No, that was just to make it easier. It's what, like 2.58 or something? 2.56.
it's so complicated.
Yep, well, it's great. Perfect. Looks great. Looks great. Yeah, that was awesome. Exactly. Okay, what did we enter? What are we entering into our inverse t here? How much area do we want to the left? 0.005, 0.5% split. I mean, it's 1% split across two. So half of that 1%. And then what are our degrees of freedom here? 7. And what we see is negative 3.499. Perfect. I just want to showcase what was the, I know some people calculated this, the z-score was like 2.57, 2.58-ish. Yeah. If I change my degrees of freedom to be 30, well, actually 30 here isn't even all that close. If I change my degrees of freedom here to be like 100, then we're getting closer and closer and closer and closer to that value. So actually the 30 metric isn't even, that good. And we see, this gets larger and larger. Closer and closer and closer and closer. And 30 is just when we're saying it's good. All right, but absolutely correct. This is 3.499, corroborated by the table that we will not have access to. All right, questions with figuring out our relevant t-scores. Much exactly like z-scores, but just inverse t. So any questions here? All right. Then let's take a look at this kind of in action here. So we are told that a survey was given to 10 students and found that the average amount of sleep that they got each night was 7.1 hours with a standard deviation of 0.78. So standard deviation of 0.78. Does it say anywhere that that is the standard deviation for all of students sleeping? No, that's just for the 10. So this is our S being equal to 0.78. Now, if it did say population, if it said that the population standard deviation was 0.78, then that would be sigma instead of S. And instead of using our t-scores, what would we use? We'd use these scores instead. Right? So if we are given population standard deviation, regardless of sample size, we're good to use Z. And technically, if the N was like 50, you could use Z or T. You're going to get about the same answer. Doesn't really matter. All right. And then this little bit of like assume the variable is normally distributed doesn't matter. That's not an assumption that we need to make. It's cool, nice that you're giving us that, but that's not relevant to what we are doing. All right, so let's go ahead and figure out what's going on. We need to figure out what our T of alpha over 2 is going to look like. What are my parameters going to be for my inverse T function here? What area am I looking at? The 2.5%, so 0.025. And then how many degrees of freedom do I have? 95% confidence interval. Yeah, 9 degrees of freedom. And so I get 2.262 for my t-square. So if we have a 95% in the middle, how much are on my edges? Yeah, 2.5%. What's our sample size? 10 minus 1. Yep. Do we feel good with how I've labeled my information, why I'm using the variables that I'm using, and then how I got my t-score? Yep. Yep. And we want that, but positive. Yeah, 2.262. Yeah, just like busy. And we're going to use a negative version and a positive version when we do the error. We'll subtract it once and we'll add it once. Okay, how do I calculate my margin of error, my error bound around the mean? you know, hypothetically, just if I were to ask you on like a test or something, what the margin of error is, how would we do this? So it's gonna be, we said t-score times the sample standard deviation divided by the square root of n. It's perfect. Which in this case will be our 2.262 times 0.78 over the square root of 10. And double check this on your calculator. Think this works out to be 0.0 or 0.558. And actually by double check this, I mean, I'm gonna enter it in here. So I'm gonna turn this positive, and then we want to multiply this by 0.78 divided by the square root of 10, 0.5579. So 0.558. Do we feel good about where the error is coming from? How we're calculating this? Why we're doing what we're doing? Okay, so that's the error, but we're not looking for the error. We're looking for the confidence interval. But our confidence interval is just going to be, we take our mean and we subtract the error for the lower bound, and then we take our mean and add the error for the upper bound. So it's going to be that 7.1 minus what we got for the error for the lower bound, and then 7.1 plus what we got for the error for the upper bound. So from 6.54 to 7.66. And what's our interpretation here? What do we know? Or what are we trying to say? What does it mean that this is our 95% confidence interval?
The number was.
How sure are we?
That
95% sure that the
number is in between the.
true mean lies somewhere. Yep. We are 95% sure that mu lives here. Yes, yeah, exactly. 95% confident that that is what we're saying. Mhm. Well, so we had to calculate the error, and then we converted the error. We added and subtracted the error to get the upper and lower bound of the interval. A quick thing that I want to note, I didn't see this on many people's quizzes, but I did see this on a handful. Always go lowest to highest. So your lowest bound should be your smallest value, your upper bound should be your largest value. Otherwise, you're going to get something that doesn't make sense. I don't think that was a mistake that I saw in many people, but I did see it on a handful, so I did want to mention. Now, of course, we did this by hand for z-scores as well at first. Wasn't too bad to do this by hand, not too horrible. But what did we just end up doing after a while? Using the calculator. So how did we do this in the calculator to do z-scores? So just stat, actually, yeah. So stat tests 7. Well, what's that right under 7? What's that under our z interval?
Oh.
No. I mean, what's right under That's the T interval. Oh my goodness, it's the thing that does the thing, but for the other thing. Okay, so we're gonna do the exact same thing that we did with our Z interval, but we're going to use the T interval here. And we're just going to enter in the data into the stats that we have. So 7.1 for our mu, or for our X bar rather, 0.78 for our standard deviation. We said this was 10. We wanted a 95% confidence interval, and it gives us, lo and behold, the exact same thing that we already calculated. Cool. Are you using a Z interval or a T interval? Yeah, still doing stats. We don't have data yet. Yeah. Mhm. Mhm. Mhm.
But I didn't know like the numbers that got me, they just got, they got.
It's just gonna be a calculator thing. All right, questions with our confidence intervals with T-scores? All right, take a stab at this second example here. Now, when you can just go ahead and plug it in to get the interval. But to prepare you for things that I could ask, go ahead and also find me the relevant T-score. So the T of alpha over 2. And then give me the error as well. You don't need to use the error to compute the confidence interval. You can just do that with your calculator. But give me both of these values in addition to giving me the confidence interval here. One thing that I do want to note before you start, are we given the sample standard deviation? No, what are we given instead?
Average.
So that would be the mean. We're given the sample variance. How do I go from variance to standard deviation?
With the decimal point.
Square.
Yeah, use. Variance. Yeah. Yeah, no, those are-
But no, you're S squared. Yeah, so 10, yeah, that should be right. This looks great. I don't think I actually changed that. I think you did 100. I think you did 100 when you entered it into your. Yeah, so that should be. Uh, 0.0.
It's a sample, it's variance. So. So it's like, yeah, it's a T of alpha over two. Alpha over two.
Are you on time? Yes, I'm on time.
By figuring out.
Yeah.
Straight. And then just work out that.
Yeah, I just like to go.
That's fine.
He must be nineteen. Oh my god. This is.
Yeah. So that's the second step, right? That'd be the final answer. That's the.
Double check your degrees.
I do this.
This is the. The 162 is the X bar, not the average. So it's N.
Oh.
N minus 1.
Bro, what is this? I think it's. And I just said this to like the right now because you can't even read your own handwriting. Like that's the code. The bad thing to do this. It sounds kind of bad.
The 165.
Look nice.
4.38.
Oh, yeah. Press exit out. Okay, at least you can go. So I tell you.
Yeah.
Are you enunciating every syllable?
What do you mean?
Yeah.
This is great.
What did you use?
What's yours? Yep, otherwise it's.
All right, let's take a look at what we've got here. What is our, how do I find my t-score? What is the area that I should use here? .05 for my 90%. And then how many degrees of freedom do I have? 15. All right, so 1.753. I've seen a lot of people rounding to 2. I'm not going to say that that is objectively wrong. I'm going to round our t-scores to 3 just because it's a little less precise than the z-scores. So having a little bit more precision is helpful with these. 1.753. Yeah. That is what no, it should not be negative. The T of alpha over 2 is always. Thank you. All right, for my error calculation, that is our 1.75 times our 10 divided by the square root of 16. 3826. Yeah, if you round, you'll get the 25. Okay. And then what did we get for our confidence interval? Yeah.
Divided by.
Standard deviation of the sample, yes, divided by the square root of it. Yeah.
So. Know the sample variance is 100 degrees.
Yes.
Drops. Okay. So would the standard deviation of the sample would be.
Samples, so sample size would be 16, yeah, and then, yeah, so N would be 16. And then what would S be? Yeah, square root of 100. Which is, yep. Yep. What we get for our interval? And then, perfect. All right, questions with our T-sample stuff or T-score stuff? Yeah, probably. So if we're looking at a 90% confidence interval, how much area is trapped between? One second guess. How much between? For a 90% confidence interval. So we've got some kind of distribution, not necessarily normal, but theoretically, if we took a big enough n, it would look normal. We're looking for the two values that are going to trap 90% of our area. So between these two t-scores, this is the negative t-score, this is the positive t-score, we have 90% of our data. Say again. So overall, there's 100% of our data. So this area right here is 0.9. That's in between. But our calculator doesn't process center area for inverse t. If it were inverse norm, we could set it to center and just use the 90% and we'd be done. Right? But instead, our calculator only uses area to the left. So instead, we need to figure out what is this area. Well, if I have 90% in the middle, how much am I going to have on either side? 5%? Yeah, exactly. 5% on the left, 5% on the right. And so this would be inverse t of that 0.05, that 5%, with however many degrees of freedom, in this case, that 15. Or if I wanted to use this t-score instead, how much area do I have to the left of that rightmost value? Yeah, exactly. That would be 0.9515. And you'll get the exact same answer, but it'll be positive instead of negative. Yeah. Good question. Yeah, you could use 0.95 for the area and it would give you the positive value of t. Yeah. Any other questions? All right, one final example to look at. This time, rather than being given statistics like what is S, what is X bar, and whatnot, we are instead given a series of data. And we're being asked to construct the exact same thing, find the 99% confidence interval, blah, 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 blah. We could go through this and do the exact same process. We would need to know what is X bar, what is S, what is, well, N we know is going to be 7, right? So we could find X bar and S. And so we'll start by taking a look at that. There's nothing wrong with that. In this case, to enter in my data, we're going to stat and edit. And we're going to enter in exactly what we have, just like what you see here. Okay. How do I find information about this data set? So if I wanted to know things like the median and the standard deviation and the mean and the Q1 and the Q3 and all that fun stuff, where do I have to go that takes this data set and gives me that information? Stat, calc, one variable stats. Very good. And we get a whole list of things. Yeah, so you need to enter in the list like what I had. Yeah. Yes, you need a list. Yeah. Okay, so what pieces of information do we need from here? We need X bar, which in this case is 70.
You don't have.
Do you have a decimal? I would maybe double check the values that you entered. One of them might be off by like 1 or something. Or one of mine might be off by 1. I don't know.
Oh, it is mine. That's how.
Yeah. Mhm. Frequency, all, or you just ignore that. You just hit calculate. Yep. Frequency list is cool, but not one that we're going to use. Yes. Yes, yes, yes. So like is it supposed to have like a, it's supposed to be 16.1 and
Yes.
blah, blah, blah. Yeah.
You just put
So I would do to 3. 3 would make a lot of sense. I've been doing 16.145. So that is the sigma if what we are using is a population.
okay.
So that's assuming that it's a population and not a sample. So we can't actually use that. It's a good idea. But not how we can use that. So in this case, you'll notice pulling from S, not sigma, we get the 16.145. And now we can do exactly the same thing that we've been doing up until this point. We have all the information that we need. So we're going to stat tests t interval. And we want our, we said X bar to be 70. S to be 16.145. And we set a 7. This is 99. Confidence level, confidence interval level. That's cool. That's awesome. It's in the problem. Yeah, it's in the problem. It's 99%. Yep, enter. And we get that this should be from 47.38 to 92.62. 0.38, goodness.
So we don't have to do inverse T.
That would be if you were doing it by hand, you do inverse T to get the T. I mean, I could ask you, right, like what is the T of alpha over 2, and then you could get that. And then I could ask you like what is the EBM, and you would have to figure out the calculations for those. But since this is just asking for the confidence interval, I made you do that twice. We're good. Now, I think a lot of people said that that was already entered. That might have already been entered just from like the previous people. But also your calculator will pull from the data to run these calculations. So for instance, if we were going, well, I can't, I don't know about that. If instead of using statistics that we calculated from one variable stats, you instead told it to use the data. So again, going to stat, going to tests, going to our T interval, and telling it instead, hey, use the data from L1, it will give us the exact same thing that we got when we actually plugged in X bar and S. Yeah, frequency of 1 is the same as everything has an equal frequency. You should get a range of values. Don't hit enter twice, you're hitting enter once.
Yeah, I got like X bar.
You should have an interval like this. It should be from 47.38 to 92.62.
Yeah, but for me, I got all the values that you want to go through in my head. Except for the fact that I got support the because my gas I have it from 5.0 columns. Not the same. But very. Yeah, basically, you're.
Give us another discovery.
Yeah.
It's called land experience.
That's right. That should be.
Oh, yeah, see. No, yeah.
Wax it.
Oh, that's all that.
That's nice. That's really amazing. To get on the playlist. They do like that. Actually, I think that's a good site.
Any questions about our T-scores? We have about 15 minutes left. I'm going to give you guys the rest of this time to work on your 6.2 classwork. So if you have any questions as you're working through that you would like to go over, more than happy to do so. But beyond that, you guys have the rest of this time to work. No quiz over this. The test over Unit 6 will be on Wednesday of next week.
You can get like a pack of colors.